Okay, so the next thing we're going to look at is instantaneous rate of change, and how that's related to what we were just doing, average rate of change. So instantaneous rate of change. So far in our mathematical careers, if you haven't had calculus before, we've only been able to find the slope of a line. And calculus is going to give us the tools that we can find the slope at any particular value of any function, if it exists. And so instantaneous rate of change. First, I'm just going to give you kind of the background with it. So let's say we have this function. It kind of looks like a cubic. And let's say we wanted to find the instantaneous rate of change. Let's say x equals a. Let me just arbitrarily choose where x equals a is going to be. Okay, so that means I want to find that slope, what's happening, what's this rate of change right here on this graph. And so I could figure this out by choosing a value that's close to x equals a. So maybe choose some value right in here. And so if I looked at this and I joined the line between those 2 points, I can see that this might give me a little bit or close to what the slope is at this point, but not, this looks steeper than what this slope would be here. But it's an estimate. So let's choose a value even closer of x, closer to x equals a. So maybe I chose some value c, and c is going to be closer than b is to a. So maybe c is right here, our y-intercept, or x-intercept. So if that's the case, when I chose and I find the slope, it's not as steep, but it's looking a little more accurate. So we're going to keep doing this. So we're going to get it so that distance in between that value of the other point that we're choosing close to a is so small, minuscule, that it's basically going to give us the slope. So we're going to keep choosing an x value closer and closer. X equals a. Where the distance between those two x values is going to 0. I wish I could scroll this up. Which is between the two x values. Going to 0. Okay. So this is kind of giving us what's going on, intuitively what's going on when we're finding this instantaneous rate of change. And so let's go back to this find difference quotient, or find the average rate of change. An example. F of x equals x squared minus 4x plus 1 on the interval value we're starting with is a. The second x value that we're ending in, finding the average rate of change, is a plus h. So we need to find those 2 points of those lines, or find those 2 points. So we need to figure out what is f of a. So all you're doing is you're going in and plugging in a wherever you see an x in your function. Go in wherever we see an x, we're going to put parentheses. So parentheses squared minus 4 times parentheses plus 1. Put a in the parentheses and simplify if possible. That doesn't really simplify, right? Write it as a squared minus 4a plus 1. And so now let's look at f of a plus h. Let's make our parentheses a little bit bigger because we're going to have to put that whole expression a plus h in there. So parentheses squared minus 4 parentheses plus 1. Okay, so I notice I can simplify this down by expanding things and, if possible, combining like terms. So if we squared out a plus h times a plus h, that would have it if you wanted to say that was a squared plus h squared. That's not right. Let's distribute the negative 4 inside the parentheses. So negative 4 times a is minus 4a. Negative 4 times h, so minus 4h plus 1. So if you had distributed a plus h times a plus h, we would have gotten a squared, an ah plus an ah, so plus 2ah plus h times h squared minus 4a minus 4h plus 1. I'm wondering if this looks familiar to you. A little bit. F of a plus h minus f of a.
Difference in square?
What did you say?
It looks like difference in squares to me.
Yeah,
Or
but
sum of.
you're right, Trevor. So it looks like the difference quotient or just the slope. So this is a plus h minus a. So f of a plus h. Notice that in the denominator, the a's cancel. We're left with h. We've already done the work above. So the f of a plus h. It looks nasty, but this is going to simplify out. Normally they kind of look ugly, but they simplify out really nicely. So this is equal to our a squared plus 2ah plus h squared minus 4a minus 4h plus 1. Then we had to subtract off this f of a. The f of a was here. Be careful because this is minus that whole piece. So it's minus. That negative has to distribute to each piece. So to save room, I'm going to distribute the negative. So I'm going to get negative a squared. So really it's going to be plus 4a minus 1 all over each. Again, it looks nasty, but if you notice, there's going to be a lot of things that start canceling in that denominator. We have an a squared minus an a squared. Those go away. I have a negative 4a plus a 4a. Those go away. I have a positive 1 minus a 1. So those cancel out. And so notice that the terms left in the numerator all have an h in it. Right? We have an h here, we have an h squared here, we have this h here. So we technically can factor out the h in the numerator. So if you pulled out that h in the numerator, we would have, pulling it out of 2ah, we're just left with 2a. Pulling it out of an h squared, we're left with a single h. And pulling it out of negative 4h, we're just left with minus 4 all over h. And our h's cancel. Sorry, it's a little messy. And so our answer, because the h's cancel, we're just left with what we had in that numerator. So we're left with 2a plus h minus 4. And remember I was talking about, we're choosing that value of h to be very, very small, getting closer and closer to 0. So later on, we're going to see that we're just going to plug in 0 for this h. And then we have the slope anywhere on the line to a minus h. So depending on what x value we chose, we'll just plug it in for a, and that will give us that slope there. Pretty darn cool, right? Okay, so this brings us to...
Yeah, so Professor, so like what did we exactly find? So what is this equation?
So what we had found was the average rate of change just between two generic, so in an interval, a, comma, a plus h. Let me actually pull up Desmos, because Desmos is a feature that you guys, it will be helpful for you to use throughout the semester. There's times that we want to plug in numbers that are close to zeros, like 0.01, 0.001, 0.00001. And so doing that and having to plug it in for x could get really, really kind of tedious. But I also want to show you what's going on graphically with this equation. So let me pause and pull up Desmo, and I'll start the recording again. Okay, so the graph that you see right here is the parabola.
We're still on your whiteboard.
Darn it. Okay, let's do this. I'm sorry, I thought you guys were looking at what I was doing. Okay, so now you see the parabola that is in front of you, and that was what we were just trying to find, the average rate of change of the function x squared minus 4x plus 1. Was that right? Yes, it was. And it was on the interval a, comma, a plus h. So I was telling you that this is giving us, how to find the slope at any particular point. So looking at this graph, so let's maybe say x equals 5 here. I'm going here. So I don't know if you can see, but I'm up here at x equals 5. Okay, so notice, in here around x equals 5, you can see that that graph is increasing, right? So when we find the slope, that should be positive, because we know things are increasing when the slope is positive. Also, we can see that it's really increasing anywhere from x equals 2 to positive infinity. I noticed that the slope, when we're closer here to the vertex, is not as steep, right? As the slope over here when we looked at x equals 5. So now let's go back and let's plot the line at x equals 5. So I'm going to go over here to put in the equation, and I'm going to keep the parabola in here. And so x equals 5, what we were doing on the interval, we were letting x equal a. And so we found that the slope was 2a plus h minus 4. So we have y equals 2 times A, but we said it was 5. Minus 4. That's not going to help you. I was thinking I was, let's try 2x minus 4. Okay, so it really, really depends on where we were. This was our A value though. So really, if I did that, that would give me 6. So that was telling me my slope is 6. If my slope is 6, I can find the equation of the line because I have this point. And I should have chosen one that I knew what the point of the line was. But so I would have y is equal to 6 times x. And I would have to figure out what my b value is there. So maybe I didn't really choose the right kind of point. But basically you can see, and we'll be able to find the slope anywhere on this by plugging in the value of x. And so basically our slope when x was 5 is 6. Notice if I chose a value on the other side of our vertex, left side of our vertex. So let's say 0. We can see that the graph is decreasing here, and we can see that we'll have a slope that's negative. And so if we plugged in 0 into that equational line that we had just found for A, we would have 2 times 0, which is 0. I told you that h value is getting infinitesimally small, so we could treat that as 0 minus 4. So the slope when x equals negative or 0 is negative 4, which we can tell that it's a decreasing slope. Notice that if we plugged in, and our slope when it's changing directions on our graph should be 0. And if we plugged in this point where it's 0, when x equals 2, you'll notice if we plug it into that 2a minus 4, we get back 0. And it does. It gets us 2 times 2 is 4, 4 minus 4 is 0. So really what we just found is going to give us the slope anywhere on this curve at a particular point. And we're going to discuss this in different ways throughout the next few lectures, if not next few weeks. So if you're not getting it quite yet, hopefully as we go through more and more and kind of saying it in a little bit different way, that it will all kind of fall together.
So we basically created a formula that would give us the average rate of change for any point on this graph.
Basically the instantaneous rate of change. So exactly what is that slope at any x value on that graph?
Yeah, depending on how big the h is, and that's your decision. You can put in.
What we're going to be doing is making that h infinitesimally small, continuing to get closer and closer to 0. And so we're going to treat it really like it's 0.
I see. And so we can do this process to any other equation, and then we basically find that formula for that equation that would help us find the instantaneous rate of change.
Yep. So basically what you're going to be doing is using the difference quotient with any of the functions it gives you. And we're going to be making that h value go to 0. And so we're going to treat it as, once we've simplified down that difference quotient, we're going to just plug in 0 wherever we see a h left. And that will give you the equation to give you the slope anywhere on that function where it's defined.
Yeah, so the difference quotient is like the average rate of change version of derivatives, right?
Yeah.
Yeah.
Well, by doing that, getting it to where we zeroed out h, we basically did find the derivative, did we not?
Exactly. So zeroing out the h, you're basically is the instantaneous rate of change, and you're finding the derivative. We'll use the term limits, say that's telling us what that value is going towards, and we're going to let that value of h go to 0. But I think you're going to have to wait till next week until we talk about really limits. But you guys kind of got an overview. This is almost done with 2.1. So I'm going to stop the lecture for today just because we only have a couple minutes, and I won't be able to.
before you go, I have a question.
Yeah.
So I noticed that there was assignments due from the winter or sorry, fall semester from last semester.
Let me stop recording.